We probably should think about getting started here. So everybody's gathered their food and sustenance. Well, I'd like to welcome you all to our annual colloquium on the history of science and technology. These have been a lot of fun over the years, and I hope you've had a chance to see them before. Today our speaker is Dr. Samantha Thompson, who's a curator and historian at the National Air and Space Museum. And her subject, as you can see, is television as an aid to astronomy, the rise and fall of the image tube. And this is a fascinating chapter in instrumentation, which I saw the tail end of before the development of the familiar CCD and CMOS technology that we use in our instruments today. But the thing that's fun about it, there are interesting lessons to be drawn from technology that didn't quite take off fully. And that's something I think we'll hear about. Dr. Thompson received a BA in astrophysics from Berkeley and a PhD in the history and philosophy of science from Arizona State University. And her CV includes prior stops at Lowell Observatory and the American Institute of Physics. We're delighted to have her here with us today. Dr. Thompson, please.
Thank you so much. See if the mic's working. Testing, 1, 2, 3. Is it coming on? Yeah, it's good. Maybe not. 1 second. Oh, we're good? Okay, thank you. Thank you all for coming out today. I really appreciate it. I appreciate always talking to astronomers. It's a field that I've both stepped away from and towards in a different direction. So happy to have you kind of hear about this era in astronomy that not many young astronomers know about, but I'm happy to give it a little bit of attention that I think it deserves. So I'm going to start with this instrument right here. So in 2013, Smithsonian Magazine published their 100 objects that made America. The list included artifacts representing some of the greatest accomplishments and discoveries in American history, from Meriwether Lewis's silver-plated compass used to map the Rocky Mountains, to a vial that once contained Jonas Salk's polio vaccine. One object, this one here, is a 3.5-foot tall instrument enclosed in a case of metal, which was used by an astronomer to revolutionize our understanding of the composition of the universe. From the late 1960s to the early 1980s, astronomer Vera Rubin and her colleague Kent Ford, who had only a few years earlier designed and built this instrument, traveled to several observatories, attached their new observing aid to telescopes, and recorded the internal motions of several dozen spiral galaxies. Rubin and Ford discovered that the outer arms of each galaxy were rotating at speeds that should not have been possible given the amount of visible mass. Possible explanation was that some unknown material that did not shine or reflect light the way stars or dust do had to be present in the galaxy. This study was the first real strong evidence found for the existence of dark matter. Rubin was able to find evidence of dark matter in part because of the research project she pursued, and in part because of the instrument she employed. Rubin noticed that few other astronomers were interested in the rotational dynamics of galaxies, which attracted her to the problem. In the male-dominated field of astronomy, Rubin chose the project with little competition that she could really develop on her own and she could tackle at her own pace. As Rubin was forming an interest in the outer bands of galaxies, she was hired at the Carnegie Institution of Washington's Department of Terrestrial Magnetism, where Kent Ford was there looking for a research program that would push his newly developed spectroscopic camera to its limits. With Ford's instrument, which employed new photoelectronic technology to more efficiently observe very dim objects, Rubin could record the motion of fainter stars with shorter exposure times and without the need of observing on the largest telescopes. While the benefits of using an instrument that could amplify the light from a distant object were apparent to much of the astronomical community, as seen in conference proceedings and correspondence with image tube developers, astronomers' initial uptake of the device was limited. Though a few astronomers did attempt to use Ford's instrument in the late 1960s and throughout the 1970s, with varying degrees of success in acquiring scientific data, the technology failed to gain widespread use and support. So if you go to Griffith Observatory in Los Angeles, you'll find an exhibit on the history of astronomical imaging and the advances in astronomical detectors. The exhibit takes you from the eye to photography to CCDs. Not represented in this narrative, however, is the role of image tubes in astronomy. While a largely forgotten technology because it never fully replaced photography as a primary means of detection, before CCDs came on site, photoelectronic imaging still led to huge advances in our understanding of the universe. So I want to start with this background about the state of astronomy in the mid-20th century that kind of places, what were astronomers debating at the time. So during the first half of the 20th century, telescope design really appeared to approach a limit in size, restricted largely by funding and material constraints. In 1948, 2 decades after George Ellery Hale secured $6 million from the Rockefeller Foundation to construct a 200-inch telescope at Mount Palomar, the telescope saw first light. Jointly operated by Carnegie and Caltech, Hale's telescope was lauded for its observing power, but even as it was being constructed, some astronomers began questioning the usefulness of investing resources in such large-scale projects. In his 1943 presidential address to the AAS, astronomer Joel Stebbins, a leader in photomultiplier technology at the University of Wisconsin, raised the issue of the law of diminishing returns in astronomy. Stebbins noted that a telescope twice in size may cost 10 times as much to build, but the resulting gain in light gathering power and resolution would not necessarily be proportional to the size or cost. In 1956, Washburn Observatory astronomer and Stebbins' protege, A.E. Whitford, similarly argued that, quote, "The astronomical telescope has long since reached a state of perfection where the tranquility of the atmosphere rather than the quality of the optics determines the image quality. The astronomer may, in theory, gather more information by increasing the aperture, but the engineering difficulties and the cost both rise steeply for any considerable increase in size over that of existing telescopes. Only a select group of astronomers would have access to the large telescopes like Hale's privately operated 200-inch, and few, if any, other astronomers' institutions could afford to devote the resources to constructing such a rival instrument. The apparent size limit of optical telescopes restricted astronomers' potential opportunity to see further. Some astronomers and physicists believe an alternative to constructing larger telescopes was to amplify the incoming light or increase the sensitivity of the telescope's recording device. Whitford argued that, quote, "The final link in the information chain, the radiation detector at the focus of the telescope, is therefore the element which must be scrutinized for possible lack of efficiency. If the efficiency is low, improvements can be counted on as equivalent to increasing the aperture of existing telescopes." If offered the money for a 100-inch telescope, many astronomers, Stebbins asserted, would have the, quote, "moral courage" to say that they prefer to build an 80-inch telescope and use the remainder of the funds for improved instrumentation and better operations. He argued that if the law of diminishing returns seems to prevent us from doing something better, we can always try to do something different. Combining advanced instrumentation with modest-sized telescopes could have the effect of giving more astronomers access to adequate observing resources. Only small improvements in imaging techniques were needed, Stebbins and Whitford concluded, to open new research opportunities for a wider field of astronomers. Imaging technologies have also seen a great advance in astronomy. Early astronomers could only sketch what they saw, drawing what their eyes detected through the lens of a telescope. In the late 19th century, astronomical research underwent a transformation in observing practice when photographic plates replaced hand-drawn images of the sky. In the late 19th century, newly available dry gelatin-based photographic emulsions really revolutionized astronomy. Photography not only provided a permanent record, but also allowed for integration over extended exposures. Stebbins and a small group of specialists began exploiting in the early 20th century photoelectric principles to measure stellar brightness. The accuracy of this method far exceeded that of photographic methods, where the response was nonlinear and therefore required constant calibration. The disadvantage of this technique was that only one measurement could be made at a time. To overcome this disadvantage and take advantage of the benefits of the photoelectric principle, astronomers looked toward image tubes and the electronic detection of astronomical images. By the 1950s, there were several methods employed or proposed to electronically amplify light coming from an object. Devices which used the photoelectric effect to convert photons into electrons that could then be manipulated to produce a brighter image are generally called image tubes. Television tubes are a type of image tube, and like others had advantages and disadvantages for astronomical work. Television tubes had been proposed for use by astronomers since about the 1930s. At the 1933 meeting of the AAAS, when astronomers discussed using television to extend the range of telescopes, one astronomer suggested that the 200-inch telescope, then still under construction, if aided by a television-type camera, could be made equivalent to a 2,000-inch mirror. Newspapers throughout the United States printed articles detailing the new reaches of space that would be made observable through the use of television. American newspapers described the hype, awareness, and excitement of television's potential use in astronomy, with one article imagining, quote, Mars and its canals projected as a disk a foot in diameter, the frontiers of the universe pushed out several 100 million light years, stellar distances measured with an unheard of accuracy, new revelations of the structure of the great nebula in which we live and call the Milky Way, the vistas open are endless. With the TV camera, astronomers saw the potential to really increase the light gathering capability of telescopes. Astronomers imagined that they could use this technology to make more efficient use of the light, again, rather than building a larger telescope. During the middle of the 20th century, while some astronomers still continued to campaign for even larger telescopes, quite a few chose to look ways to really advance the recording side rather than the light gathering side. In 1951, astronomer Somschalton, in collaboration with the Cambridge observatories, carried out tests with a standard television tube, the image orthicon, to ascertain any possible advantages over photography alone. Initial results using the moon as the subject were very encouraging. Direct comparison of the two, as you can see, shows enhanced contrast in the image with the television technique and greater detail. This is largely just due to the shorter exposure time that was allowed. Quantitative tests were performed, determining that television was also superior in sensitivity, resolution, and efficiency. Early experimental work with television cameras proved to the astronomical community that television systems could be employed to the benefit of some astronomers. The promising results, though, of these initial tests encouraged others to further develop, test, and build other electronic detectors that could be routinely used in observatories. These results piqued the interest of Bill Baum, an astronomer at Mount Wilson, who had experience developing photometers while working with optics and electronics during World War II. Baum initially began testing signal-generating tubes, which are television tubes, like the image orthicon and vidicon, at the 20-inch site testing telescope on Mount Palomar. He had success evaluating the different devices and determining their limitations, but in the end he determined that these commercially produced tubes were not good enough for astronomy. Though TV tubes had the potential to combine the technical advantages of photomultipliers with the spatial information provided by photography, they also had, for example, poor resolution and difficulty resolving scenes with small differences in contrast. Other astronomers eventually came to the same realization. Bill Livingston had the most advanced orthicon system at Kitt Peak. He used the system longer than anyone else. He studied the sun, but also eventually gave up on it as well, though in his case it was largely due to managerial decisions rather than technical decisions. By the late 1950s, astronomers had begun to realize and accept the limitations of commercial television tubes and sought to design tubes specifically for the needs of astronomers. But they still had to rely on television companies with optoelectronic capabilities. Joel Stebbins started writing to RCA and Vladimir Zworykin, one of the inventors of television. And Bill Baum approached EMI and was put in contact with Jim McGee, who built the first electronic working television in England. Astronomers were also able to connect with electronic specialists in the military, which were utilizing this technology in great abundance in the 1950s. During World War II, the same physicists that developed commercial television were used in efforts to build television-type detectors that could detect heat exhaust from enemy aircraft. Ultimately, development in these two fields, both TV and military, where funding was much more abundant than it was in astronomy, provided astronomers with the confidence needed to attempt to utilize the same systems and helped advance the needs to build better detectors specifically for their community. What began in earnest in the 1950s were numerous efforts to employ image tube technology in astronomy, each with different resources, different design philosophies, and different potential users. The devices they produced also ranged widely in feasibility and usability. The path to adapt this technology for astronomy was not easy, though. One example I like to use, I think neatly illustrates the frustration that came from a lot of astronomers. In 1950s, Yerkes astronomer Albert Hiltner consulted with an RCA engineer about the possibility of developing a detector. After considering the problem, RCA suggested that the quickest answer was for astronomers to purchase 100 photomultiplier tubes, which RC also produced and sold, and situate them in array to provide spatial data. This would have been a very large detector and would have required extensive calibration and engineering to make work. Like many electro-optical companies, RCA wanted to expand their consumer base and sell more products, but they did not want to invest in the resources required to design a device that was really only needed for the specific needs of a relatively small consumer base. Today, I want to focus on one version of this technology that developed that kind of got the most use, and that was this camera developed by the Carnegie Image Tube Committee. It operated from 1954 to 1976 and was developed by President Vannevar Bush, who during World War II led nearly all of the United States civilian military research and development. After the war, he articulated a highly influential vision for the relationship between science and government in the United States. Bush brought together a group of astronomers, physicists, and engineers he thought could really meet this challenge. The project was coordinated through the Carnegie Institution's Department of Terrestrial Magnetism. While singular in structure, this group collaborated and learned from members from observatories and laboratories from the US, England, and France. Their goal was really unique in this field, which I'll talk more about in a little bit, but it was to create an electronic imaging device that could be of use to the general astronomical community. They envisioned a device with enough gain to be beneficial to really engage in any research project, but whose operation was simple enough to be employed by any astronomer at any observatory. During its first decade of operation, this committee worked with industrial and military laboratories, private and public observatories, and individual astronomers to develop an image tube that they could market to the astronomical community. By 1964, after a 10-year period of research and development, the committee decided they developed a tube that was ready for astronomical research. Their tube did receive some modest use and helped astronomers acquire groundbreaking scientific results, including those of Rubin and Ford, but the technology was never fully adopted by the astronomical community. And what I want to talk to you today about is why did that happen? During World War II, older astronomers were often hesitant about adopting the many new technologies that had arisen from both world wars. They often lacked the technical training to utilize newly discovered electronic techniques. Younger physicists and astronomers who received training during military service, particularly during World War II, were needed to move into the field of astronomy to direct instrumentation development. The story of the Carnegie Committee really starts with two physicists at Mount Wilson, who both became important figures in determining the direction of development of image tubes at the Carnegie Institution. Ira Bowen, first, worked for Nobel Prize winning physicists in graduate school and used his laboratory experiments to help astronomers understand observational data. He was teaching courses at Caltech in 1946 when Bush chose him to direct the Mount Wilson Observatory. He was the first physicist to do so. Bill Baum gained much of his experience in electronics during World War II. He graduated at Caltech, but was interrupted. His education was largely interrupted by the war. And during his service for the Navy, he learned to develop instrumentation, mainly those with optical and electronic components. Bowen hired Baum to help Mount Wilson Observatory astronomers use and develop electronic instrumentation. They had similar backgrounds, studying physics and developing optical instrumentation, and both believed that electronic instrumentation, which had been spurred on development by wartime needs, could be used to push observations deeper and dimmer. Bowen and Baum differed, however, in how they viewed the role of the Carnegie Institution in taking a larger leap in the development of electronic imaging. Because of their different roles and responsibilities, Baum was really the only one that could actively press for the development of this technology at Carnegie. Bowen was restricted by the environment in which he became director and the pressure put upon him by his staff to focus on astronomers' research. According to Bowen, development efforts should be left to commercial industry, but Baum, on the other hand, was influenced by the relaxed nature of technological development during the war and believed that commercial companies could not be relied upon to create something specifically for astronomers' technical needs. Baum had to wait until the fall of 1953 to propose image tube development to Carnegie Institution President Bush. Bush would make an annual visit to Pasadena and would just start knocking on doors and talking to various staff members. When Bush stopped at Baum's office, he updated him on instrumentation efforts and really made his argument that Carnegie needed to play a large role in the development of electronic imaging. Bush took Baum's proposal back to Washington, D.C. to see what might be done to organize sufficient talent and funding to make it happen. After Bush's visit to Mount Wilson and his discussion with Baum, it's a lot of B names, but Bush and Bowen corresponded. They wrote many letters back and forth. Initially, Bush and Bowen proposed that Carnegie collaborate with EMI, the British version of RCA, while simultaneously establishing a US-based group. Bowen's concern was the time any development efforts would require of his staff. So Bush went to the Department of Terrestrial Magnetism and director there, Merle Tuve. Tuve was also very concerned with staff time, but he still believed that someone could do something within Carnegie if given the right staffing. Bush's main concern was the scientific prestige of the US and of the Carnegie institutions in particular. The Carnegie Corporation, of which Bush was a board member on, granted him $50,000 to put towards this new committee to develop this technology. Eventually, EMI declined collaborating with Carnegie, and Bush was happy to keep the focus centered in the US itself. With the Carnegie funds in hand, he made Tuve director of the Carnegie's Department of DTM, the chairman of the new committee. At the US Naval Observatory, Bush found John Hall, an astronomer who had the right experience and characteristics. At the National Bureau of Standards, he located a physicist called Bill Martin, who was becoming known for his work in electron microscopy. Martin was also an engineer at RCA laboratories in Camden, New Jersey. And with these two institutions, the National Bureaus of Standards and USNO, he found really keen partners. The next step was attaching an astronomer to the project that had one of the leading authorities, Hall became their leading astronomer on the project, which Bush thought was needed to really entice the astronomy community at large to give this project credibility. I switched these two slides, so apologies. In their first year of operation, the Carnegie Committee encouraged and supported image tube development already in progress, but they found most efforts would not satisfy a wide group of astronomers' needs. The developed devices tended to only be of interest to small, specific groups. As early as 1936, André Lallement, an astronomer at the Paris Observatory, predicted the quantum efficiency considerations that gains by a factor of 100 over conventional photography could be obtained by using the photoelectric effect. He spent nearly 15 years on photomultipliers. Not satisfied by those, he moved on to kind of create an electron camera and created his first working camera in 1951. The system where photoelectrons were directed to impact an electron-sensitive photographic emulsion. It's called electronography. Subsequent work was devoted to improving the performance and reliability of the electron camera. The system had the benefits of very high definition and was also very light, which means that it could be placed at the primary focus of the telescope. It was also acknowledged at the time, though, that preparation of the camera for a night's work was lengthy and laborious. The photocathode was actually destroyed after each use, and it took about 24 hours to set up the system again. But astronomers who used it were generally encouraged by the results obtained. Lallement, along with Maurice Duquesne, worked closely with Merle Walker and Jerry Crone at Lick Observatory. They studied the rotational rates of the Andromeda galaxy and found a very rapid rotation close to the center of the galaxy using this camera. Lallament's camera was also used extensively in France, and it was used for the last time at the Canada-France-Hawaii telescope. So it was used for quite a few decades. Jerry Crone made a more advanced version of this camera by creating a valve that allowed the photocathode to be preserved after each use, but it still required some technical expertise. In early assessments, CITC members, the Carnegie Committee members, realized that they would need to direct the course of development efforts if they hoped to define a device that could really be used by any astronomer. Each type of image tube had the potential to solve the problems astronomers were interested in, but technical concerns appeared most prominent in early discussions. The committee also determined, for example, that a tube they produced would need to be significantly easier to use than the Lallement system. In deciding on which tube to develop, the committee had to consider the availability and location of the resources, most importantly, technical staff. And for about 10 years, they ended up doing most of their research and testing at Lowell Observatory. The committee's strongest partnership was with James Dwyer McGee. He was an Australian-born, Cambridge-educated physicist who took up a job in the newly established television industry after completing his PhD. McGee was uncertain at the time that the industry of television would go anywhere, but he really wanted to stay in England, and jobs were scarce at the time. At EMI, he developed the first working all-electronic television system. During World War II, he helped create some of these infrared camera tubes. During this time, McGee also worked on reducing radar noise in storage tubes, as well as electron multipliers. But as the war drew to a close, his thoughts and attention returned to television and making a satisfactory cathode potential stabilized camera tube. Even though McGee advocated for EMI's version of their main television tube over RCA's image orthicon camera tube, the RCA tube eventually became the standard in television cameras. And our fun fact for today, the Image Orthicon camera tube, its nickname was the Emmy, and that's why the Emmy Awards are called the Emmy Awards. So astronomers were using these cameras that became the face of the television industry, which had much more of a focus on science when it started. McGee was also becoming increasingly bored with commercial television, and everything changed for him when he was invited to Palomar to see if EMI could help aid astronomers. EMI wasn't interested in taking on a project for such a small consumer group, but McGee was very interested in this new endeavor, so in 1954 he decided to actually move away from the television industry and into academia to start a group working on photoelectronic devices at Imperial College London. He realized that special tubes of this type were required for scientific purposes, but in such small numbers that commercial laboratories were not interested to develop and make them. In order to spread his ideas about the benefits of image tubes, McGee organized a symposium on photoelectronic image devices as aids to scientific observation. He was extremely proud of this symposium, which would occur 5 times during his life, and felt that their most useful activity had been to provide a center unrestricted by commercial or military secrecy, where research could be carried on and students trained in the field of applied physics. The first meeting was held in 1958 at Imperial College and was largely a success. At the time, he was able to attract a small number, mainly physicists, from a variety of disciplines, including medicine. In 1961, he organized the second symposium, attracting twice as many contributors as the first. This growing success reflected McGee's growing reputation in the international community of astronomers and applied physicists. McGee's work, while important to only a relatively small group of people, quickly became an essential part of research. When the staff of Lick Observatory was moved to Santa Cruz in the mid-1960s, their use of the Lala-Man camera had to cease because it required constant attention to maintain. This made the tubes that McGee had been developing at Imperial College more appealing as they were simpler and easier to use. The first signs of frustration from the astronomers came early. After the 1954 Moscow meeting of the IAU, like the prior meeting, 1955 in Dublin, a special session was devoted to photoelectronic imaging, and the Carnegie Committee presented their status, along with members of other groups from the United States, France, and Russia. After the meeting, Michigan astronomer Leo Goldberg, in a report to the IAU, expressed his concern that the French and Russians were further along in development compared to the US-based groups. Tuve replied directly to Goldberg, expressing his own frustration with Goldberg's response and others he had seen to their development of image tubes. Since Lala-Man had built the first image tube for astronomy 2 decades prior, some astronomers thought image tube development should have been more progressed. Tuve defended his group against the accusation of being too slow in their progress, arguing that there was nothing stopping any astronomer from using the French tube, even though it was the committee's impression that this camera would be suitable only for enthusiastic participants, he said. The committee, Tuve argued, was directing their efforts toward an image tube more generally useful. They had established at their start that they wanted to design a robust, easy-to-use image tube that could be used by any astronomers. But astronomers, evident by Goldberg's letter, wanted something sooner. At the IAU meeting, Russian scientists presented tests performed with a micro-window tube, which were not, as Tuve informed Goldberg, a new device at the time. Tuve's group had investigated micro-window tubes and described their development efforts in the annual Carnegie Yearbooks, a publication which likely did not attract a wide astronomer readership. The micro-window tubes were in fact available for immediate use by astronomers, but the Carnegie group abandoned further development because of their poor resolution. Tuve contended with Goldberg, suggesting that, quote, "If we supply you with a tube such as the Russian used, I honestly believe you would test it for half a day or so and set it aside. if we supplied you with one of your colleagues with a Lalaman tube with sealed off cassettes of fresh cesium surfaces, I'm confident its best use would be as an exhibit at the observatory shelves. And we are bringing one to our new museum, so I can attest it's still true. Our committee, TÜV argued, was not endeavoring to make a grandstand play, but was interested in producing a genuinely useful astronomical tool for wide regions of the spectrum. Though frustration by the dissatisfaction of astronomers, TÜV concluded in his letter with a diplomatic request for feedback from astronomers. He wrote, "I write this somewhat reluctantly, as I feel rather immune to criticism of astronomers regarding image tubes, but I recognize that our committee is vulnerable, and especially the two astronomers on it. If you can help us make the United States astronomical leaders somewhat less discontented with the present situation, I will appreciate your suggestions." TÜV was relatively reserved in his response to Goldberg in comparison to his plea to Ira Bowen, however. To Bowen, he wrote, "I suppose our committee should be content to be lambasted by our American friends, but I'm strongly tempted to throw the ball right back at them with the reminder that no great help was forthcoming from the ranks of astronomers, either for our efforts or for other folks working on the same project." TÜV was frustrated that the committee could not secure the services of newly graduated astronomers to assist with the tedious process of testing image tubes. In every attempt they made to recruit a young astronomer, that astronomer was always given a job somewhere else where that position was permanent. Bowen acknowledged that he had received several reports from astronomers after the Moscow meeting, and though he did not specify which astronomers had approached him, he suggested to TÜV that either the committee had not been fully promoting their own accomplishments, like the French or the Russians, or that astronomers do not really understand the problem at hand. While creating an image tube that can produce large amplifications of light was relatively easy to accomplish, Bowen recognized that the committee's goal was bigger. Bowen questioned whether the reactions to the Moscow meeting did not point to the desirability of appointing an advisory group of perhaps a dozen or more astronomers that could guide TÜV's progress. Bowen's suggestion of an advisory committee implied a search for advice, but his focus seemed to actually be on educating astronomers rather than in taking feedback. This really shows the focus on the dissemination of information rather than having a dialogue between the instrument builders and the instrument users. Both Bowen and TÜV seemed to suggest that if astronomers knew the true state of affairs in the development of image tubes, they would be satisfied with the suggested destination and the progress. Suggestions of ways to improve the committee's outreach were not received with much consideration by Merle TÜV. In response to Bowen and the astronomers who had turned to him, TÜV asserted that he had heard from astronomers and that many of them were actually aware of the possible developments in the field and had many problems that they were eager to apply this new technology to. TÜV was in this really interesting situation of trying to maintain that there was interest in the technology while trying to downgrade a lot of the criticism that was coming at him. TÜV argued that the outcry from astronomers was not due to their frustrations with the US group's lack of progress, but their eagerness to use one of the tubes. Because of this, TÜV concluded that there was no need to consult with astronomers as to the direction of development, and instead he argued time should be dedicated solely to the rapid development of the image tube itself so that they could get it into the hands of astronomers. This assessment really contradicts TÜV's letter to Goldberg, which insinuated that a large problem was that Goldberg and other astronomers did not have a good grasp on the actual problem facing tube developers. The resistance from both groups of users, the Carnegie Committee and the astronomical community, to work together to determine a common goal and plan is really evidence in this correspondence. Though the non-leaders, astronomers like John Hall and Bill Baum, and others scattered across the country, may have felt differently, who had personal relationships when they were testing across many US-based observatories. In the end, in development efforts, the committee really continued to work towards their goal without really any good input from the astronomical community. The original Carnegie members had established their goal in 1954 to develop this rugged device. And by 1964, after a decade of research, they finally thought they got there. They wanted more time on the project, but the pressure coming from the astronomical community was too great. The Carnegie Committee contracted RCA to produce 2 different types of image tubes that the group believed were ready for regular astronomical use, a Mica window converter and a cascaded image intensifier. The Mica window converter was particularly useful for astronomers wishing to observe in the infrared, but the cascaded image intensifier was Carnegie's general use image tube. This tube was produced at a higher quantity than the other and became known as the Carnegie image tube. The first run of the Carnegie image tubes each cost about $5,000 to produce, about roughly $40,000, $50,000 now to manufacture, but would be provided free of charge to customers. This happened through a grant from the NSF. Between 1965 and 1968, the Carnegie Group loaned image tubes to 34 observatories around the world. Initial reactions were positive, and the CITC had plenty of demand and quickly allocated all available tubes. Of all the available Carnegie image tubes that were allocated, some were used actively by astronomers, some garnered intermittent use, and some were largely neglected. A few cases pulled from correspondence and oral history interviews showcases the difficulty the group had in having tubes regularly used at observatories. First, in December of 1963, Lick Observatory astronomer Tom Kinman requested a replacement tube after their tube had begun to produce so much spurious background noise it became useless for any observational program. Kinman wrote, quote, "We have tested it in the same spectrograph as the other Carnegie tube, which we possess, and find that the background is quite excessive, even at 17,000 volts. Apparently the background is so bad that the test spectrum was swamped and we do not know whether a focus is obtainable. The tube has therefore been packed, ready to return to you. Needless to say, I'm very disappointed in the performance of this tube, and I hope that it will be possible for another tube to be made available." Kent Ford, who was responsible of coordinating all of the test tubes, responded quickly, equally disappointed in the tube's failure, but suggested that it was inevitable that an occasional one should build up excessive background. Kinman was frustrated again within 6 months of receiving his replacement tube when the new tube again began producing more background. Ford was sympathetic and likewise frustrated, noting that Kinman's tube was producing backgrounds unlike anything he had encountered. He could not find any reason for the tube's failing and recommended that Kinman look to purchase a tube directly from RCA, as the committee had ran out of tubes to spare. It is unclear to me whether Kinman purchased additional tubes from RCA, but he never obtained scientific results that were published with the Carnegie image tube. This episode highlights that even a skilled operator like Tim Kinman had difficulty with the tubes in practice, likely in part due to the inability of the RCA laboratories to produce standardized tubes to the Carnegie's specifications. At Mount Stromlo Observatory, located near Canberra, Australia, interest in the Carnegie image tube came largely from Theodore Dunham, who had worked at Mount Wilson Observatory. Kent Ford traveled to Australia to assist in the installation of the image tube system, and according to a 2013 interview with Kent Ford, Dunham was more interested in getting the image tube assembly actually set up than using it for scientific research. Ford trained both Dunham and Kurt Gottlieb, the observatory's instrument manager. In Ford's mind, he noted that there were no issues in training either men, but I had heard later that Gottlieb rubbed some people the wrong way, which made people not want to actually use the device because they needed that technician's help to do those observations. The most successful use came from the Carnegie staff members Rubin and Ford, who shared an office at the Department of Terrestrial Magnetism campus. But even Rubin, when first offered a use of a CCD spectrograph, offered to move away from the image tube, and CCDs quickly became the standard use in astronomy. Though their image tubes received mixed results, the earlier hope that the Carnegie tube would replace photography alone was dashed. The group was unsuccessful at meeting the goals they had established at their formation, and they laid the groundwork for a new era in observational astronomy by showing that there was a need in the community for more sensitive and efficient detectors. In attempting to serve a conduit between producers of image tube technology and the potential users of that technology, the group had to compete for commercial resources and contend with choices made by individual astronomers. The efforts of the group show how the backgrounds of several key physicists influenced the direction of image tube research at the institution, and how the concern of scientific prestige led the Carnegie Institution to decide to investigate image tube technology to begin with. The increase in US federal funds helped this effort sustain itself through 2 decades of development, but could not ultimately contend with observing habits and researchers' needs of disparate groups of astronomers. While the Carnegie's efforts did not result in an overwhelming adoption of image tubes, by examining how the image tube was produced, funded, marketed, the story can shed light on the many and varied processes through which astronomers have acquired or ignored new tools. Thank you.
Thank you very much for that very interesting talk. There are many familiar themes there we encounter in all our instruments. Can I take some questions, please?
Yeah, so when I saw your title, I was drawn to thinking about the Vidicons that were aboard the IUE. Mm-hmm. Are those related to these? I thought they were sort of UV-doped versions of this.
There is a strong connection there. So these are that signal generating television tube. A lot of what I've talked about here and what I work on is largely what the ground-based astronomers were working on. Vidicon tubes were more useful with space-based because they allowed that transfer. You can actually get photographs. So those developed far beyond.
Did they pick up from the Carnegie tubes, or were
they picked up from like the image orthicon trail. So in image tubes, you have the signal generating tubes, which are TV, like image orthicon and Vidicon. The Carnegie tube was actually a phosphor screen tube, and then you had electronography as kind of a third wheel, if that makes sense. So the technology is all kind of being designed at the same time, and different tube designs were used depending on what the need was for that.
In the early 70s, there was a very successful version from Alec Boxenberg's group from the UK. I wondered if that came out of McGee's work, or...
This, his work really, it didn't come out of McGee, so it was kind of a different group working on things. And this is part of what I started to encounter, was that you had a dozen different groups working on their own very specific tubes to serve a very specific use in astronomy. And it would maybe help, 1 or 2 research groups. And what the Carnegie group was trying to do was make a tube that everyone could use, which was also not helpful.
Too ambitious.
Yeah, that they found out.
Boxenberg's device seemed to work for all sorts of different projects, imaging and timing and spectroscopy.
Yeah, and I think that's where, McGee's project was the same. There was tubes designed out of, you're still getting them out of Russia, but at the Greenwich Observatory, they were developing tubes there as well. So you get these little factions, and they all kind of start to fail at the same time. But they were used successfully for a very long time, but you still had a lot of those similar issues of you needed someone with electronic experience.
Yeah, there was a
in
whole
order to
Boxenberg's army used to take 12 people to Palomar and so on.
Yeah, I think that's a really good example, is if you had the setup in place, if you had the technicians in place, they could be used really successfully. If you didn't have them, then that became a problem. And I was able to speak to Vera Rubin once before she passed away, and that's what she told me. She liked going into an observatory, and she was the one who knew how to operate everything, and she didn't have to rely on a technician to help. Where a lot of the other astronomers, if you wanted to use something, you needed that trained technician. And for astronomers, especially coming out of the 1930s, 1940s and 50s, that's not how you do astronomy. That's not how you do observation. You start introducing these new components. So yeah, I think Boxenberg's is a good example of where you can get great success, but for a limited time and under limited circumstances.
Well, we have two questions. Why don't we start with Charlie and then we'll come to Brian.
If the CCD had never been invented, what do you think would have been the trajectory of this line of technology?
Should never ask a historian to say what if. No, it's when I talk to astronomers about, why they stuck with this technology for so long. They say it's because it was really obvious we needed something. Like photography alone was not cutting it, so this filled a gap. It's likely as younger astronomers came on board that did have that technical experience, it would become more routine to use this every day in observations. But it's not clear to me that this was the real move forward. Still have an issue of funding, that this wasn't a big funding opportunity, but if it became the only one, maybe that would have made it more interesting. I think of where you get this pivot is with the Hubble Space Telescope and trying to decide which instrument to put up or which detector to put on the Hubble Space Telescope. And that's really what drove that final difference. So I honestly don't know what would have happened, but what is clear to me is that this was filling a gap and a need. Though I will say, those early arguments for instead of building bigger telescopes, we'll just build better detectors, that clearly didn't happen, right? We eventually figured out the telescope issue and we kept building bigger and bigger telescopes. And even Vera Rubin continued to use the Carnegie image tube on the biggest telescope she could get. So it wasn't making it easier for university astronomers who only had access to a 60-inch. They were still being used on the largest, so grand goals.
So you have a question from online. We'll come back to Brian.
Yeah, from the chat, Nelson Caldwell. I used a Carnegie image tube mounted on a spectrograph at Saratoga 1-meter telescope in the 70s for my thesis work. That one was considered an excellent device and very popular, though it was on a very small telescope. Similar tubes were used on the KPNO 0.9-meter, 4-meter, and the Tololo 4-meter spectrographs, being phased out in the late 70s by SIT Vidicons, followed by CCDs in the late 80s.
Yeah, that's amazing, and I'll email you about that. But there were 3 of these image tube spectrographs built. One was at Kitt Peak, one was largely used at Lowell Observatory, and then one was used at Saratoga. And I don't know where that one is. I hope it's still there. If anyone's ever down there, if you see something that looks like this, I'm searching for it. I know where the other 2 are.
Okay, so Brian, you had a question.
Can you say something about how did the data get recorded?
So usually you're dealing with the same system. With what I've been talking about is you end up with a photograph at the end of the day. So you're still dealing with photography at the end. Eventually you start to get digitization coming in and talk about that aspect at all. But for most of the 50s, 60s, 70s, you're still getting a photograph. So it's really interesting with things like television technology where you have the image would appear on a screen and then you'd have to take a picture of that screen. So you lost so much data in that transfer. And I think this speaks to why it wasn't as helpful for a long time also, because you really needed that direct transfer of data to get the most use out of the 2. That's a good question. I'll give that.
You have one more?
It's actually from me. Somebody mentioned the IUE satellite, and you would get a tape with the spectrum. That was all very nice. But astronomers really wanted to see the image, so they would generate an image on a piece of plastic that you could look at.
We have the engineering model of IUE that we hope to put on display in the new Astronomy Gallery when our museum reopens. And I have those images. And if anyone can help me explain how to explain that image to the general public, that is the biggest problem I'm dealing with right now. Because it is interesting. It's like it adds an extra element, I'm guessing, for astronomers, but for visitors, man, that adds another step you're putting in there. So that's really interesting. We should chat about that.
Okay, Charles, I guess this is our last question.
So first of all, thank you. But how was CCDs introduced? Because it seems to have happened much more quickly when that threshold was crossed.
So I don't know the full history here. What I do know is that I'm going to tie it again back to the Hubble Space Telescope. And that became the real impetus to move in the direction of that technology. And you're starting to get interest from a wide variety of fields in that technology also. So I talked about astronomers being a really small consumer group in image tube technology. You have medical experts interested in this technology for imaging as well. But with CCDs, there seemed to be a wider consumer group. So you had more funding going into it because of that. Robert Smith's The Space Telescope goes into it a little bit more for space-based astronomy, but I haven't done enough research to give you a solid answer. But it does seem to have happened really quickly versus the story I'm telling, is a 40-year-long history.
Thank you.
Yeah.
I want to thank our speaker again. Thank you. And there's cookies and some tea in the back, so if anybody would like to stick around and talk.